In this lecture, we are going to cover mesh analysis for the analysis of circuit networks. And what I want to do is first go over the steps for a mesh analysis of a circuit network. And these are very simple. If we follow these steps each and every time, then we will never get a mesh analysis incorrect. Of course, in a mesh analysis, what we're going to be solving for are the loop currents. And the loop currents are associated with what we call the independent loops in a circuit network. And again, the set of independent loops is the minimum set of loops in the network graph which will cross all nodes and branches in the graph at least once. So it's the minimum number of these loops gives us the set of independent loops. So I have a circuit up here on the upper right, which gives us it's a two-dimensional circuit, so it's composed of a simple graph. And the number of loops in this network is just simply the number of holes in the network, which we see is going to be 4. But we have first identified then the number of independent loops for that particular network would be 4. Next, what we're going to do is we're going to label the loop currents on the circuit. And when we're labeling it, we're going to indicate the direction of current flow for the loop current path. So here we've labeled the 4 current loops. And I've indicated with arrows the direction of current flow. And these loops then flow through the loop currents flow through all the branches of that loop. And when you have branches such as the branch up here with the IX that share multiple loop currents, then what we see is that that is a superposition of the loop current I1 flowing to the right and I4 flowing to the left. So IX would be I1 minus I4. All right. Next, we identify the controlling values of controlled sources as a function of loop currents. So in this circuit here, I have an IX. IX, as we just saw, was a function of the loop currents. That is, IX was equal to I1 flowing to the right minus I4 flowing to the left. So I would identify that controlling value as a function of the current loops. At this point, we'd be ready to start creating our L equations. And the way we do that is first we apply our current constraints. That is, we constrain the loop currents by any current source. That is, a current source constrains the current on that branch to be that current value. So for example, I have this 2 amp current source on this branch to the lower left of the circuit, which constrains the currents on that branch to be flowing 2 amps flowing up. All right, now it constrain the loop current I1 flowing through that branch. We also have another current source, was a current-controlled current source. So the current flowing through that branch is going to be 2IX flowing up. Now it would constrain the loop currents I3 and I2 that are superimposing on that branch. Okay, once we do our current constraints, then the next thing we do is we would apply KVL around our independent loops. But we're going to apply KVL around independent loops that do not contain a current source. Why? Because KVL states that the sum of the voltages around that loop must sum to 0, but we cannot predict the voltage across a current source. That is, that the voltage is going to be determined by the remainder of the network, which at this point we're not ready to predict. So we cannot predict the voltage across a current source directly, so therefore we cannot apply KVL around those loops. So we would apply around all independent loops that do not contain a current source. Next, we would enforce KVL about a superloop that superimposes loops containing connected interior current sources. What we mean by an interior current source is we're going to define that as a current source which has more than one loop current flowing through that source. If there's only one loop current flowing through the source, such as this 2 amp source, only has one I1 flowing through it, that is not an interior source. Okay, so I would not need a super loop containing that. However, this 2IX is an interior because it contains loop currents I2 and I3, and therefore I would have to form a super loop. What we mean by connected interior current sources, if I had another current source, say for example, on this 20 ohm. If that was a current source as well, then these two would be connected then as they would be sharing a node, and I would have to form a super loop. The way we do that is we would then superimpose the independent loops that share these set of connected current sources. Once we've done that, we will be guaranteed to have L equations for our L unknowns, and we would be ready to solve this set of equations for the L unknowns, which would be our L loop currents. Once we have our loop currents, then we superimpose those loop currents in any branches, and we can then uniquely specify our branch currents. Once we have branch currents, we can specify any branch voltages of the networks by enforcing either Ohm's law, that branch contain a resistor, or we can use KVL to find voltages across things such as current sources. All right, so let's work through an example. So here we have that network that we had in the previous slide. Let's go ahead and solve for the loop currents in this network. And so let's follow our steps. The first thing we need to do is identify the number of loops. And we said before, the number of loops for a 2D simple graph is just the number of holes in the graph. And I have 1, 2, 3, 4 holes in this network. So I have 4 loops. Next, we need to label these loops, and we're going to label them by identifying a current. So I'm going to call this loop 1, and I'm going to use an arrow to identify the direction of current flow through this loop. So this little diagram here is basically specifying that I have a loop current flowing through these branches, all 4 of these branches in this loop. Okay. All right, and they all contain I1, and these branches then are all flowing in a clockwise direction. All right, then I'm going to find this next branch, this next loop to be I2, flowing again. I just chose arbitrarily a clockwise direction, I3 for the lower right loop, and then I4 for the top loop. Okay, so I've labeled my 4 loop currents, and these loop currents flow. I chose a clockwise direction, and they flow through all the branches in that loop and superimpose in any shared loops, or shared branches, excuse me. Okay, so now we've gone through the first 3 steps, and we are ready to start writing down our equations that will constrain these loop currents. The first thing is, forgive me, one step that I forgot was we need to write down our controlled sources. Controlling entities as a function of loop currents, and here I have my IX, my controlled source, IX flowing through this 10 ohm resistor, and I need to write that as a function of loop currents. IX is flowing to the right, I1 is also flowing to the right in this branch, but I4 is flowing to the left through this branch. So therefore IX is equal to a superposition of these loop currents, so I say that IX is equal to I1 minus I4. Since I1 is flowing in the direction of IX, I4 is flowing opposite the direction of IX. Okay, now at this point, I've written all my controlled sources as a function of the loop currents. At this point, I can start writing my equations. Where do we start? Well, we start with our current constraints. We have 2 current sources in this circuit network. Both of these current sources will constrain the loop currents. That is 2 amps current source will constrain I1 flowing through that branch. That is, we can uniquely say that I1 equals 2 amps, since I1 is flowing in the same direction as that 2 amp current source. This actually gives me my first of the 4 equations. Next, I need to constrain the loop currents by 2IX flowing up. Well, I3 is flowing up through this branch. I2 is also flowing this branch going down. Therefore, I can state that since this current source forces the current to be 2IX in that branch, it must be equal to I3 flowing up in the direction 2IX minus I2. Okay. And then I can, since IX equals I1 minus I4, then I can write 2IX to be 2, I1 minus I4 equals I3 minus I2. This gives me the second of my four necessary equations. Okay, so now I'm done with my current constraints. The next thing I need to do is apply KVL. So the question is, where can we apply KVL? Well, we want to try to apply KVL around each of my independent loops. So let's look at loop 1. Can I apply KVL around this loop? Well, the answer is no, because it contains a current source, and I cannot predict the voltage across that current source. So I cannot apply KVL around loop 1. All right, can I apply KVL around loop 2? The answer is no, because it contains a current source. So therefore, I cannot apply KVL around loop 2, nor can I apply it around loop 3. What about loop 4? The answer is yes, I can apply KVL around loop 4 because it contains no current sources. And so therefore, I'm going to start writing down my KVL equation on loop 4. Okay, that is, I'm going to sum up the voltages across all branches, and they must sum to 0. Now to do that, what I'm going to do is I'm going to follow the direction of my I4. That is, I'm going to write KVL around this loop in a clockwise direction, starting with this 5-ohm resistor. So the voltage drop there, I have I4 flowing into the high potential side, which I define a high potential side as I go around the loop. So it's going to be I4 times 5 ohms is the voltage drop. Then the 20 ohm, it's going to be the voltage drop across this 20 ohm resistor is 20 ohms times I4 flowing into the high potential side minus an I2 flowing into the low potential side. Then I have a voltage drop across the 10 ohm resistor, which is going to be 10 ohms times I4 flowing into the high potential side minus I1 flowing into the low potential side. So this gives me my equation for loop 4, my KVL equation. Okay. Now you notice, since I'm identifying high potential polarized such that I4 is always flowing into the high potential side, then it's going to be 5 ohms I4 plus 20 ohms I4 minus I2 plus 10 ohms I4 minus I1. And therefore, the I4 will always be positive when I'm writing the voltage drop across a resistive load. Okay, well, this gives me my third equation. And as we said before, I have checked all my other loops. I cannot write KVL around loops 1, 2, or 3. However, what I recognize is that I have an interior current source, 2IX, which has 2 loop currents flowing through it. So therefore, I need to write a supernode, which is the superposition of these 2 loops. I can take I2 and superimpose it with I3 around that current source. Okay, and so what I get is I get one loop that then contains the current source, but doesn't, or it envelops the current source, but does not contain the branch of the current source. So I just superimpose these 2 loops. So what I see here is if I look at loop 2, right? If I had KVL around this loop, then it's going to sum to 0. So it'll be the drop across a 20 ohm resistor plus a drop around the current source plus a drop around the 4 ohm resistor would sum to 0. But by doing the super loop, what I see is that I can't express this voltage here directly. But what I'm going to do is I'm going to say, well, okay, well, this voltage is equal to the voltage drop across the rest of this loop, which is just that across the 2 ohm resistor. So there's no mystery about the super loop, but rather what it's doing is I am extending this branch voltage to the remainder of the loop. Okay, so that's how that works. So now I can write my KVL around the perimeter of my super loop. And to do that, I have the voltage drop here. I'll start with the 4 ohm resistor. It's 4 times now I have I2 flowing up minus I1 flowing down, plus 20 ohms times I2 flowing to the right, minus I4 flowing to the left, plus 2 ohms times I3, which is flowing down. All right, so that gives me my fourth equation for my, which now is going to allow me to solve for my 4 unknowns. Okay, so what I can do is, I can use whatever method I want to solve these 4 equations. I can use substitution. I can use write this as a matrix equation and so forth. here what I did was I just threw this into a MathCAD worksheet in a solve block. Okay, so I'm going to solve for I1, I2, I3, I4. So I initialize these. Remember, that's the colon, shift colon gives me colon equals. These are assignments, so we have to initialize these variables under this guess value portion of the solve block. Then this is a control equal when I'm writing my actual equations, which it calls constraints. So I write down equation 1, I1 control equals 2 amps. Equation 2, 2I1 minus quantity I1 minus I4, control equals I3 minus I2. And I write my KVL loops. I included units in here just because it's nice to be able to do that in a solve block, so I can just keep track of all my units for my quantities. You don't have to, but it makes it easier to read. So for my KVL loop, 5 ohms, which is shift W, then control G, gives me my capital omega, times I4 plus 20 ohms, I4 minus I2, and so forth. Control equals 0. I write down my super loop equation, and I use the find command to solve for my 4 loop currents. And so I get to I1 is 2 amps, I2 is 1.16 amps, I3 is 2.698 amps, and I4 is 1.209 amps. Okay. So then at this point, I can find any branch currents, like IX would be I1 minus I4, and I say it's about, that would be, I1 was 2 minus I4, 0.209, so it looks like it's 0.791 amps would be IX, or I could find a voltage drop across any of these branches by just applying basic Ohm's law or KVL. Okay, I could have also written this as a matrix. So here I define A for all these equations as a 1 by 1 matrix. So here this A is multiplied by I1, I2, I3, I4, and so forth. Okay. So this first row is 1, 0, 0 times my current vector, which is 1 times I1 plus 0 times the S times the rest equals B on the right-hand side, which is 2 amps. That just says I1 equals 2 amps. Second row says 2I1 plus 1 I2, since I moved that over to the left, minus 1 I3. Again, I move this to the left. Minus 2 I4 equals 0. And then for my KVL loop, I have a minus 10 I1. Then I have a minus 20 I2. And then I sum up the 5 and the 20, the 10 times I4, and that all sums to 0. Then the last row I have a minus 4 I1 plus a 4 plus 20 I2 plus a 2 I3 minus a 20 I4, and this all equals 0. Okay. And then I just say my current vector is equal to A inverse times B, and I get exactly the same answer. Okay. The last thing we could do is, okay, well, let's have to do this by calculator. I want to do a 4x4. Since I1 is known, that's fine. The other thing I can do is I can use that fact that since I1 is known and put that on the right-hand side, and then take everything else on the left here, and I can write this as a minus 2I1 or minus 4 amps on the right-hand side. Same thing in this equation, take my minus 10 I1, put it on the right, so it gives me 20 volts. Same thing here, I can take my minus 4 I1, put it on the right, since I1 is 2 amps, that would give me 8 volts. And I could have written this as a 3 by 3 matrix as well. Okay. And it gives me exactly the same answer, of course, where I1 is 2, which is known. And I get the same values for I2, I3, and I4. So this concludes our presentation on mesh analysis with an example. And hopefully this gives you enough leverage to solve any circuit that you want using a mesh analysis.